The next item to discuss with polynomials is really what happens in the middle. And like I said in the previous video, that's the zeros, which means we're really going to be talking about the x-intercepts. So let's just, for example, let's say I have some polynomial and it sort of does something like this. It comes into the graph here. Let's say it comes back here and maybe it goes back around. Let's call that 4. So these points here, these have a couple of names. They're called the zeros and they're called the x-intercepts interchangeably. But most of the time we'll be using the word zeros. And what this tells me, this actually gives me some information about the equation of the polynomial. So for this graph here, I could say, well, I know that the polynomial has those zeros, which really means, if we're thinking about parabolas, which we spend a lot of time with, and quadratics, this means that it has these factors. X minus -1, so really x plus 1, x minus 2, and then x minus 4. So notice if you set this equal to 0, you would actually solve for each of those intercepts. This isn't quite correct though, because technically I don't actually know what scale this graph is, so I should really add the letter A there just to represent that this could be stretched out or shrunk or reflected, all sorts of stuff. But the point really of this discussion is to show you that we can get each of these factors based on the graph. And this is called the factored form of a polynomial. So for the most part, we'll be dealing with factored form in this video, and I expect you to give your answers in factored form most of the time as well, rather than standard form. Okay. So let's just take a look now at an example. And let's just say find the zeros of the following polynomials. So let's do f of x equals 7, 2x minus 3, x plus 5, and then 9x plus 4. So essentially what you're doing here is you're just setting the entire function equal to 0 and solving. But really what that comes down to, you can kind of skip this step, because really what this comes down to is we're really saying 2x minus 3 equals 0. And solving, we're saying x plus 5 equals 0, and then solving. And we're also saying 9x plus 4 equals 0, and then solving that as well. And so if this was the problem, find the zeros, I just did that. Notice how this 7 in front doesn't actually do anything. This does not have any effect on zeros. It's just there, like I was saying before, to kind of scale things. Another one I want to do, and the reason I want to do this will become apparent in a moment, I'll mention something, is let's say I had -3x, and then let's do x minus 2 and x plus 7. So notice how there are 3 x's here. There's an x right there, and right there. The second x's might be kind of obvious, right? X minus 2 equals 0 means that x equals 2. And then x plus 7 equals 0 means that x equals -7. Those are two of my zeros. But this first x here is also a 0, and it is the 0 that is 0. So if you were to, quote, solve this, it's already solved. But just don't forget about it. A lot of times students will forget that that first x is there and not include it. So I'm just pointing out that if that x is 0, then the entire function will also be 0. So it is also a 0 or an x-intercept. Now at this point you might, in a typical problem, go ahead and start graphing. So you'd have -7, you'd have 0, and you'd have 2. You'd have to determine end behavior and that sort of stuff, but it would probably look something like this. And you could then find the zeros. Okay, so that's just sort of the intro to it. That's just finding zeros if it's in factored form. But there's another situation we sometimes have to worry about, and that's something called repeated zeros. So let's talk a little bit about repeated zeros. So let's say, for example, I'm given a function, a polynomial function that looks like this, x plus 1, and then x minus 2, but I'm going to square it. Now in this case, if you were to solve each of these factors out, you would see that x equals -1 and x equals 2 are the zeros. However, the x equals 2, 0 is squared. And the x plus 1, 0, the x equals -1, really just has an exponent of 1. I'll add a little 1 in there. That number there is called the multiplicity. Multiplicity, yep. And in this case, we would say the multiplicity is 1. The multiplicity for 2 is actually 2 in this case. So the 1 and the 2 is where I got those numbers. And that's because if I took x minus 2 squared and expanded it out, it would look like this. And so that just means it shows up twice in this polynomial. And so what happens when you graph this is it actually looks a little bit strange. So I'm going to have -1, I'm going to have 2. And when I graph this function, it actually does this. So notice at -1 here, the graph just goes straight through. That kind of looks like I'm saying this is not correct, so let's just not do that. Graph goes straight through. Whereas over here at x equals 2, it sort of touches and then bounces off. So it just touches it. And it kind of looks like a parabola. It isn't exactly a parabola, but it kind of looks like one. Whoops. Parabola, not pola. Okay, let's look at another example. So let's say instead I did a polynomial. Let's go with x plus 1 cubed and then x minus 2 squared. So now we would say the zeros are -1 and the multiplicity of that is 3. And we also have 2, the multiplicity of that is 2. So if you were to graph this one, it's going to look very similar. Whoops, yeah. So we're going to have -1 and 2. But instead of just going straight through at -1, the graph kind of looks like this. It sort of has a squiggle to it. And then it's still going to bounce off there because the multiplicity is 2. So at x equals, I'm going to color code this like the last one. At x equals -1, it's a squiggle. There isn't really a formal name for this, so I just call it a squiggle. It kind of looks like a cubic though. And over here at x equals 2, we still have that sort of parabola looking thing. And this will be true for all odd functions. So all the odd powers. So let me go ahead and just kind of write this again. So for multiplicity, this is the exponent of the 0. If it's odd, the graph passes through the point. If it's even, it touches and turns around at the 0. All right. So let's take a look at a couple more examples because I want to add some slightly more difficult situations. So let's go ahead and let's determine all zeros and their multiplicities. For the following. Okay, so the first one is going to be f of x equals, let's go with -6, x plus 2, x minus 1 squared, x minus 3, and then 2x plus 5 cubed. All right, so let's go ahead and just start solving for this. This would be x equals -2. This one is x equals 1. This one is x equals 3. And then solving this is a little bit more work. -5 divided by 2, so it's going to be -5 over 2. And so you would say, okay, all the zeros are -2, 1, 3, and then -5 over 2. And then their multiplicities actually, let's just leave it like this. So the multiplicity of -2. Notice how there's technically a 1 here, so its multiplicity is 1. For the 1, the multiplicity is 2. For 3, it's still 1, and then -5 over 2 would have a multiplicity of 3. Okay, so that one's a little bit more straightforward. Let's try to add some more wrinkles to the mix. So in the next one, let's go with let's change it up here. N of x equals 3x minus 1, x squared minus 4, x minus 4 squared, x squared plus 9, and then x plus 9 squared. So you'll notice I'm deliberately being tricky in this example. That's why there's all these squareds and squareds and squareds and everything. But hopefully this will illuminate my point that I'm trying to make. So the first one, pretty straightforward. If you solve that, you get x equals 1/3. Its multiplicity is going to be 1. For the next one, if you solve this, you actually end up with plus or minus 2. And if you factored x squared minus 4, you would end up with x plus 2 and x minus 2. So there's 2 zeros there, but each one only has multiplicity 1. X equals -2 and x equals positive 2, multiplicity 1 on both of those. Now the next one would be x equals 4, but this one actually has multiplicity 2, which is shown there. Let's start keeping track of some of these. So I have this one, and I have this one, and then I have 2 zeros here. Okay, now this one's just like what we saw before, and I'm going to move down so I have a little bit more room. X squared plus 9 equals 0. If you solve this, you end up with imaginary numbers, and we're only graphing real, so really this is no 0 at all. So this factor doesn't actually add any zeros, and I don't have to worry about multiplicity because there are no zeros. Whereas the next one, x plus 9 squared, does give me a 0, x equals -9, and it has a multiplicity of 2 shown by its exponent. So just some stuff to kind of be careful of. In this case, we saw these were the sort of the new pieces here. The x squared minus 4 was new, and also the x squared plus 9 were sort of the new wrinkles I threw at you in this problem. So just be cautious of those. If you do have an x squared inside the parentheses, it's not a squared outside the parentheses, you do have to be a little bit careful. All right, so that brings an end to this first video on zeros. We'll do one more video talking more about finding